Good evening. This is Michael Covington, and this is the 10th talk in our series on Christianity and the history of science. This is for the video audience. The live audience, the actual class, already heard this talk a couple of weeks ago, one evening when I couldn't come, and Alan Haas was kind enough to fill in for me using my slides. We decided at the time it would be easier for him to do the 10th talk than the 9th. But those of you in the video audience are getting things in the right order, so here we go. The topic for tonight is quantum physics, which is covered rather well in our textbook, The Soul of Science by Piercy and Thaxton. The key idea of quantum physics is that the physics of very small objects, atoms and smaller, is different from the physics of larger objects. It's so different that it has led to deep questioning of the reality of the physical world and its relation to our minds. In other words, quantum physics is strange. Now, before we go any further, I should emphasize that I have probably less training in this area than in any of the other areas of science that we've covered in the talks so far. I know a good bit more about philosophy than about quantum physics, and that's going to color how I approach it. The motivation for quantum physics. Why is there such a thing? The motivation is first the quantization of the orbits of electrons around the nucleus of an atom. Unlike planets orbiting the sun, electrons can't orbit at just any distance. Only certain distances, energy levels, are permitted. Quantum is Latin for how much, or maybe for definite amount, or something like that. So electron orbits are at specific energy levels around the nucleus of the atom. Not just any level they happen to want to be, but only certain levels are permitted. Quantization of electron orbits is why we have the periodic table and most of chemistry. It's why we have semiconductors in modern electronics. And one very simple practical example is it's why a light-emitting diode of the most common kind drops exactly 1.8 volts and gives off red light. It's not giving off red light by getting something red hot. It's just letting electrons drop from one energy level to another and converting the energy into light of a particular color. And if you vary the amount of current through it, it changes brightness, but it doesn't change color at all because that electron transition can only produce red light of a specific wavelength. The other motivation for quantum physics is the wave-particle duality. Does light consist of waves or of particles? This has been a controversy since the time of Isaac Newton. And the answer is both. Plenty of experiments show that light is waves. Plenty of experiments show that it's particles called photons. There's technology that relies on its being both. There is technology that relies on waves. There's technology that relies on its being particles. There's technology that relies on both of them. Photographic film in a camera is a good example of something that relies on its being both. Not only photons, but other small particles, electrons, even atoms and small molecules, have wave properties. The wavelength of the electrons, yes, electrons have a wavelength, explains electron orbit quantization. In current quantum theory, every physical object has wave properties, although if the object is much bigger than an atom, the wave properties are going to be almost undetectable, or even entirely undetectable. They get smaller and smaller as the object gets bigger. Now, what is the theory? The theory is a system called quantum mechanics. It's a system of mathematical equations, models, that account for quantum phenomena. Some of the people who had large roles in making it are Max Planck, Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Paul Dirac, and others, but not Einstein. Some knowledge of German and a bit of French is handy to get through the names in quantum mechanics. And you see equations like the one on the right expressing the energy of a system in terms of its wave properties two different ways. I don't actually understand this equation. I'm not trained in quantum physics, but it's the kind of notation you see with the wide angle bracket on the right. When you see that, you're looking at quantum physics. Quantum mechanics deals with wave properties and gives answers that are probabilities, not definite predictions. As I said, any object, no matter how large, has wave properties. They are very slight for objects larger than atoms, but the point is that's what quantum mechanics, as I understand it, is about. And the predictions are probabilities, not definite. Quantum mechanics, as a mathematical system, is successful and accurate. There's technology that relies on it, for instance, semiconductors, the things you have millions of in the CPU of your computer and dozens of in a transistor radio. The problem is interpretation. How does the mathematics relate to observable reality? Wave properties do something strange. Wave properties turn into definite positions, and probabilities turn into definite states when they are measured, but not before. Until then, wave properties are simply probabilities of positions. This is the spooky thing about quantum physics. The challenge is, in some experiments, the wave properties disappear when the position of the particle is measured, even though the particle is unchanged and continues to have wave properties in parts of the experiment where the position that was measured would not affect them. This is very, very strange from the viewpoint of classical physics or everyday experience. This left people wondering whether physics, whether quantum or classical, is even real. How can an electron know to drop its wave properties when someone knows its position? Is physics all in our minds? Well, that leads us to the Copenhagen interpretation of quantum mechanics, which is now, I think, a little more than a century old, so this is not brand new science. It's century-old, time-honored science. Associated with Niels Bohr and others, the most widely held interpretation of quantum mechanics is that the wave function collapses, that is, the wave properties turn into definite positions and probabilities become actual states when a measurement is made. Now, that is a strange thing, and yet it fits observation. So, what counts as making a measurement? Is human consciousness the key to it? Does physics depend on human consciousness? If so, science is totally upside down from the positivism that I described in the earlier talks, where the external physical world is all that's real, and it almost doesn't matter whether we have minds, the world is there and has physical properties without us. That turns this inside out. But is it right? I want to sound a note of caution here. In my opinion, and I know a good bit more about philosophy than about physics, In my opinion, we are about to be looking at some professional physics combined with amateur philosophy, some of which has been unduly popular. So hang on to your seat, hang on to your hat, hang on to whatever you hang on to when you're going along a road that looks like that. This is a winding road ahead. A very strong form of the Copenhagen interpretation was proposed by John von Neumann, who was one of the pioneers of computer theory. His position was human consciousness is indeed what collapses the wave packet. Human consciousness is the key to all of physics. More commonly, the Copenhagen interpretation is we don't quite know if it's the conscious observer or the measuring instrument that collapses the wave packet, but it must be, collapses the wave function, I mean, but it must be something like that. That leads us to the infamous case of Schrödinger's cat, which everybody has heard of and nobody sees the point of. Everybody's heard of Schrödinger's cat. I must emphasize this was not a real experiment and has never actually been done. No cats have been harmed in the name of this experiment, as far as I know. If it were done, it would not give an answer. It's for thinking things through. It's a sort of imaginary experiment. It's Erwin Schrödinger's criticism of the Copenhagen interpretation. Here's the imaginary experiment. Inside a sealed box, you have a cat and a machine controlled by a radioactive decay event. That is, it's a Geiger counter or something and a sample of uranium or something. And when there's a radioactive decay event, when the counter clicks, the machine will do something. And the radioactive decay events are quantum phenomena that can only be predicted as probabilities. If the event occurs, the machine will release poison and kill the cat. The machine is constructed so it can go a decent length of time without having a very high probability of having an event. So you can leave it there for a while and not know whether there's been an event or not. According to the Copenhagen interpretation, before you open the box, the cat is in a superposed state. It has only a probability of being alive or dead, and you can design the machine so it's 50-50. The cat is not definitely alive or dead until you look at it. Strange. So does the probability become a definite state when you become aware of it? When the cat becomes aware of something, like the cat notices the machine starting to move something? What if a friend of yours is in the box with the cat? Whose awareness matters, yours or his? Does the wave function collapse when the machine reacts to the radioactive decay, even if a human isn't involved? Schrödinger's point was supposed to be that the Copenhagen interpretation is silly. But actually, this became a serious part of the weird world of quantum physics. There are other interpretations of the relation of quantum mechanics to reality. Because of the key points that some things are only predictable as probabilities, and human awareness seems to have an effect on physics, many even stranger interpretations have been offered. The many worlds interpretation is that when something goes into a superposed state, the whole universe splits into two universes just alike, except for the two states of that thing. Forever afterward, the cat is or was alive in one universe and dead in the other. You're in one of these universes, another you is in the other. This is the least parsimonious scientific theory I have ever heard. To get rid of a problem with radioactive decay, you multiply the entire universe every time anything happens. I cannot conceive of what evidence would warrant believing that. I thought the goal of science was to explain things the simplest way possible, and this is the opposite. There is quantum mysticism. There have been quite a few people trying to tie quantum physics to Eastern or New Age religions, and this has been surprisingly popular and, I will wryly say, often mistaken for science. Now, first of all, if Eastern religion can supply tools of thought that help us understand physics, I'm all for it. We know already, for instance, that Hindus knew more about logic and grammar in ancient times than Greeks and Romans did. So if Eastern religion has some tools of thought that will help us, I'm all for that. Neoplatonism already helped us. But they have to be tools of thought, not just a vague belief that anything goes or that logically contradictory things are suddenly possible because somebody said so. In popular culture, it has become common to suppose that quantum physics implies that anything is possible and is a license to believe any strange thing. You want to believe in ghosts? Okay, quantum physics. You want to believe in time travel? Okay, quantum physics, without any physics worked out. No, that is not science. There are some other interpretations to consider that go perhaps in the direction of less weirdness. Maybe quantum reality isn't actually that spooky. Here are some possibilities. There is the statistical or ensemble interpretation, which is these probabilities really are probabilities, and just as in ordinary mathematics, probabilities don't belong to individual events or states. They tell you what to expect among a large number of events. Like 1/6 of the time these dice roll 7. That doesn't mean they're in a superposed state every time you roll them. It just means that if you roll them a lot of times, about 1/6 of the time they will roll 7. And the same for quantum phenomena, according to this interpretation. There is also a family of interpretations called hidden variable interpretations. Einstein is reported to have favored this. And the idea there is quantum physics is incomplete and doesn't give us the whole picture of physics on an atomic scale. We may not be able to get the whole picture, but the point is we can't see all the way to the bottom. There is more going on deeper down. The predictions are probabilistic because they're actually predictions about things that are not at the fundamental level. Reality isn't probabilistic. We just can't see deep enough into it. Now, there is a difficulty for hidden variable theories, and I don't understand the technical particulars of this, but as I understand it, what I'm about to tell you is supported by recent experimentation. A wave property called quantum entanglement can set up an immediate relationship between two particles that persists at any separation and doesn't require any time to communicate, so violating Einstein's limit on communication faster than light. And that shows that if quantum physics is built on top of something else, that something else is not simply back to classical physics. It's still strange territory. It's just strange in a different way. Now, another interpretation that I find very appealing is a Copenhagen interpretation, but without a special role for minds. Roger Penrose and others propose that the wave function collapses. The wave properties disappear, probabilities become definite when enough other particles are affected. Even a few atoms might be enough, like the Geiger tube detecting the radioactive decay event that makes the machine kill Schrodinger's cat. That might be enough to make everything take on a definite state. I need to mention quantum computers, which are still experimental, but this is the up and coming thing in computer architecture. Experiments are being done now with computer circuits that use the wave properties of electrons to do more than one computation at the same time, then collapsing the wave function to get the answer. No, these are not something Microsoft is selling right now. They're farther out than that. They're not yet commercially feasible. They do not change in principle what a computer can compute, as far as we know. They do speed up dramatically compared to a conventional computer. They are much faster in computations that involve trying many alternative solutions because they can be rigged to try the alternatives at the same time and collapse the wave function to find out which one, if any, succeeded. Now, what does all of this imply for us as Christians? Well, my take on it is, if God wants to make strange things, let him. Christian doctrine is not tied to classical physics any more than it was tied to Aristotelian physics. It seems to be undeniable that atomic scale particles don't act like the objects we are accustomed to handling, so now we're finding out the details of that. Now, if conscious minds are essential for collapsing the wave function, what about the mind of God? Where does an omniscient deity get into, for instance, von Neumann's interpretation? It would seem that because of the mind of God, all wave functions are collapsed all the time, unless only minds in the physical universe count. I don't know if anyone has responded to that question, but I'm not well read on this subject. My non-expert opinion, well, I said I liked Penrose's interpretation. I also like some kind of hidden variable or Einstein interpretation, though not necessarily with classical physics at the bottom. We've never gotten to the bottom of physics before, so why assume we've done it now? Why does quantum mechanics have to be the deepest stage? But above all, we have to be able to say, we don't know. You can't make progress in science or philosophy or anything else without saying we don't know. Beware of the word quantum getting attached to unsubstantiated speculations well outside of real science as an excuse for believing strange things. UFOs must be quantum phenomena. Ghosts must be quantum phenomena. Well, no. Not unless you can say what quantum phenomena. Quantum physics has reopened some closed minds. Things don't have to act like familiar everyday human scale objects in order to be real. We know from Einstein that at great speeds and accelerations in masses, physics is different. We know from quantum mechanics and the evidence for it that at the atomic and subatomic scale, physics is different. Not everything acts like the familiar objects you handle every day. Electron diffraction using the wave properties of electrons is real even though we never see, for instance, diffraction of tennis balls or diffraction of 18-wheeler trucks or what have you. What can this teach us as Christians? Well, let me suggest a theological analogy, and I'm not going to run with this as far as one could, but just toss it out. If you expect electrons to act like larger, more familiar objects, you'll never get it right. You'll never get electrons right. You'll never successfully predict what they do or understand how they work. Well, in theology, a lesson that some theologians have been hammering home for 2,000 years, nearly, is that if you expect the Trinity to be just like some other object in the created universe, you'll never get it right. We can say some things about what it's not, but we cannot point to another thing that has the same ontology, the same kind of existence as the Holy Trinity. You have to use other means. In both of these cases, you have to use other means to find out what electrons are like and what God is like. So this concludes the series. I've had great fun presenting it, and I do thank you for coming.